So welcome to the lecture on vibration measuring instruments. So we have discussed vibrometer and accelerometers. As we know that vibrometer measures the displacement response of a vibration structure, vibrating structure. Accelerometer measures acceleration response of the structure. Then if we want to measure the velocity response of a vibrating structure, we can use the velometer or velocity pickups. And as we know that these pickups are the instrument that contain some seismic mass, some spring and damper element, and they are used in combination with some transducers. So if we want to measure the velocity, what can we do as a transducer? So transducer, as remember that we used for we said that for accelerometers we can use the piezoelectric materials, and that after application of the force they will give the charge and voltage, and that we can measure. So now here velocity, as we know that velocity, if we want to measure, we can use the transducer that is based on the change of the magnetic field or magnetic flux, because the magnetic flux is proportional. So there is the voltage that is proportional to the change in the change in the magnetic flux. And so what we will do with the, if we have this instrument, so we have here this body that is vibrating. So this is vibrating body, y equal to y sin omega t, and this is our instrument, and this is seismic mass, and this is the frame of our instrument. And so let us say this is, we have to use the like velometer. So we attach some magnet here. So we attach here the magnet. So these are the magnet, and then we attach magnet with seismic mass. Okay, so we attach magnet to the seismic mass, and then we attach some coils here. So these are some these windings, the coils, they are attached to the frame. So the conductor coils, they are attached to the frame of the instrument. Now when there will be the movement of this seismic mass, the magnets, there will be the change in the magnetic field in the coil, and so there will be proportionally, there will be the voltage change that will be sensed by the transducer. And because here we are measuring the change in the magnetic field, so this will measure the relative velocity z dot. So it is going to measure the z dot, the relative velocity between the excitation and the seismic mass. So what is this, and thus we can measure the velocity. response. So okay, Z is Z sine omega t minus phi. What is Z dot? Z dot is omega into Z into cos omega t minus phi. Now we know that Z by Y equal to R square by 1 minus R square whole square plus 2 zeta R whole square under root. So we can keep this into this equation, and so Z dot equal to omega into Y R square cos omega t minus phi upon 1 minus R square whole square plus 2 zeta R whole square this. So omega y, so it is omega and y, so R square. Now if we have y equal to y sin omega t, so what is y dot? Y dot equal to omega y cos omega t. So omega into y is the amplitude of the velocity response of the vibrating body, and so if we select R square by 1 minus R square whole square plus 2 zeta R whole square approximately 1, and this is possible for R much greater than 1, because R much greater than 1, so we will have here R power 4, because we can neglect 1, so this is R power 4, and also we can neglect this, and so R square by R square is about 1. So it is possible for R much greater than 1, and this is the similar case of the vibrometer, because this is the case similar to the vibrometer. As in case of vibrometer, we had taken R much greater than 1, while in case of accelerometers we took R much less than 1. So if we select R much greater than 1, R square by this term will be about 1. So what will be Z dot? So Z dot will be omega y cos omega t minus phi. So we see that the Z dot will give us the amplitude, so it is approximate amplitude of the velocity response of the structure because omega y is the amplitude of the response of the velocity of the structure. So if we see this frequency response curve for velometer, so the frequency response curve for the velometer will be same as the vibrometer or accelerometer, but we will be in the range of R much greater than 1. So as we plotted here Z by Y, and this was R, and we saw that here this okay, so this is zeta equal to 0.5, 0.7 and this is 1.0, and so we are like 1, 2, 3, 4. So usually in case of vibrometer we said that R should be greater than 3, and similarly we will follow for the velocity pickup or velometer, that in this case R must be greater than 3, and in this case we can have by measuring the relative velocity we can directly measure the amplitude of the velocity of the vibrating body. Okay, and here we have this response curve. So here we can see that although we are getting the amplitude, but except phase, because some phase will be introduced in the response because of this relative motion between y and z. There are some damper, so the relative there will be some phase, and so there will be some time lag between the response of y and z. Now let's do one numerical example. Okay, so it is said that there is a vibration pickup that has a natural frequency of 5.75. So this is Fn is 5.75 Hertz and a damping factor of 0.65. So zeta is 0.65. What is the lowest frequency beyond which the amplitude can be measured? So we want the lowest frequency beyond which the amplitude can be measured within 1% error. So case A is 1% error and case B is 2% error. So we know that z by y equal to r square 1 minus r square whole square plus 2 zeta r whole square under root. Now if we say this 1% error, so it means that if y is 1, it could be 1.01 or it could be 0.99, so with 1% error. So let's take z equal to 1.01 of y, because we are solving case A. So here 1.01 equal to, so r square 1 minus r square whole square plus 2 into 0.65 into r whole square under root. So now we can solve 1 minus r square whole square plus 1.3 r whole square equal to r square upon 1.01 whole square. So we need a calculator to solve this. So we have we can open out this. So this is 1 plus r power 4 minus 2 r square plus, so 1.3, it is 2.69, sorry 1.69 r square, and this is equal to r power 4 and there is 1.01 square. So it is 0.98. So it is 0.98 r power 4. So now we have to arrange these terms, and when we rearrange these terms, so we will have, so here r power 4, this is 0.98, so it is 0.02 r power 4, and this is minus 2, and this is 1.69, so it is 0.031 r square, and plus 1 equal to 0. So we see that this equation is quadratic equation in r square. So we will get value of r square. So r square equal to, so it is minus b plus minus under root b square minus 4ac by 2a. So minus b is, it is 0.31 plus minus under root b square minus 4 into a into c into c by 2a to a. So we will get 0.31 plus minus, and this is 0.04, and under root quantity so we will take both plus and minus sign. So we are getting 0.31 plus 0.127 so it is 10.925, and this is 0.31 minus 0.127, it is 4.575. So if we take under root, so r, and from here we will get r, this we get 2.14, and here .31. So we are getting these two values, and we have to select which one is okay, and that is correct. So as we have, this is our frequency response curve, and this is 1, and we know that we have curve like this. So if we have this curve, this is 2.14 and this is 3.31. So of course, if we say this curve is, because it is asked that what is the lowest frequency beyond which the amplitude is measured with 1% error. So if we say beyond this, so it is not possible, because after here it is 1% error, but because the curve will rise up and then it will fall to again come to 1% error at this point. So in between these 2 points, this curve is having more than 1% error, and therefore we will not take this frequency. So we will take this frequency because beyond this curve this is going to follow 1, so it is always less than 1% error beyond this frequency. So R we will select as 3.31, and that is f upon fn. So f equal to 3.31 into natural frequency, and natural frequency is 5.75. So 3.31 into 5.75. So it is 19 hertz. Okay, so here we have, based on the given error condition that we want this error, we have designed our instrument. Now the 2% error. Okay, so if we take 2% error, so we can take here 1.02 or 0.98. If we check, we will get here the R values, they are imaginary. So therefore we will take 0.98. So 0.98, it means that z equal to 0.98 of y. So we will use r square 1 minus r square whole square plus 2 into 0.65 into r whole square under root. So 1 minus r square whole square plus 1.3 r whole square equal to r square by 0.98 whole square. So it is 1.04 r power 4. So we can write 0.04 r power 4 and this is minus 0.31 r square. So we take other side, so it is plus 0.31 r square and then minus 1 equal to 0. So r square equal to minus b plus minus under root b square minus 4 into a into c, and c is minus 1 by 2 into 0.04. And this is 0.08. So we can do 0.31 plus 0.506 by 0.08. This is only valid because if take minus sign it is negative, and so we can't, we will get again imaginary. So this is minus 0.31 equal to this by 0.08. So it is 2.45, and so R equal to 1.56. Okay, so we are getting the value of R equal to 1.5. In fact, it is 57. and so R equal to F by Fn. So F equal to 1.57 into Fn, and Fn is 5.75. So we will get 9 hertz. So we are on the this response curve. We are so we were earlier 19 hertz, and now we are for 2% error we can come here. So we are R equal to 1.57. Earlier we were at 3.31. So we are here. So if we come a bit before here, so we are going to have 2% of error, and here we are 1% error. Okay. And this is R, and this is 1. Okay, so stop here, and thank you for attending the lecture, and see you in the next lecture.